In the preceding lesson, we have seen how any switching function can be implemented by means of AND gates, OR gates, and inverters. But there are other components that allow to implement Boolean functions. NAND and NOR functions have already been defined before. An AND gate is equivalent to an AND gate and an inverter, and an OR gate is equivalent to an OR gate and an inverter. Observe the symbols in which a small circle on the gate output stands for the input inverter of the equivalent circuit. The corresponding functions are defined by this table, so you can see that NAND A and B is equal to 0 if both inputs are equal to 1, and NOR A and B is equal to 0 if at least one input is equal to 1. Sometimes these algebraic symbols are used. NAND gates and NOR gates are universal modules. That means that any switching functions can be implemented using only two input NAND gates or only two input NOR gates. And this is easy to demonstrate. With a NAND gate, you can implement an inverter by connecting one input to A and the other input to 1 or to A also. The result is not A. With an AND and an inverter, you can implement the AND function, and with an AND and two inverters, taking into account the Morgan law, you can implement the OR function. Yes, as an exercise, you could try to demonstrate the same property for NOR gates. If you understand the symmetry property of Boolean algebra, it's very easy. NAND and NOR gates with more than two inputs can also be defined. So you could define a 3-input, a 4-input, and so on NAND gate, or a 3-input NOR gate, a 4-input NOR gate, and so on. Definition is the following one. The NAND of A, B, and C is equal to 0 if A, B, and C are equal to 1. The NAND of A, B, C, and D is equal to 0 if A, B, C, and D are equal to 1, and so on. As regards the NOR definition, the NOR of A, B, and C is equal to 0 if at least one of the three inputs is equal to 1. If A is equal to 1, or B equal to 1, or C equal to 1. The NOR of A, B, C, and D is equal to 0 if at least one of the four inputs is equal to 1. Nevertheless, and this is very important, the NAND function of the NAND operation is not an associative operation. In particular, a 3-input NOR or NAND cannot be implemented in this way, connecting in a series to NAND to 2-input NAND. You can check that the NAND of 1, 1, 1 is equal to 0, but in this circuit, if A and B are equal to 1, then the output of this gate is equal to 0. If C is also equal to 1, the NAND of 0 and 1 is equal to 1, so that the 3-input NAND gate generates 0, while this other circuit generates 1. And you can do the same in the case of the NOR gate. So it's very important to understand that NAND and NOR operations are not associative. As an exercise, consider the circuit made up of OR gates, AND gates, and inverters, and try to implement the same function with NAND gates and inverters. Let us see a possible solution. It's only a matter of substituting every gate on the left part by an equivalent subcircuit made up of NAND gates and inverter. For example, this OR gate can be substituted by a NAND gate and two inverters. This AND gate by a NAND gate and an inverter. The same here. We substitute this 3-input AND gate by a 3-input NAND gate and an inverter. And finally, this 2-input OR gate can be replaced by this NAND gate and two inverters. Finally, observe that here we have two inverters connected in series, and here also, and they can be replaced by simple connection. This is the reason. Now, a rather natural question: why do we use NAND gates or NOR gates instead of AND and OR gates? Perhaps the first reason is that if we use off-the-shelf components, for example in the laboratory, we only need one type of gate instead of two. But the most important reason is this one. In CMOS technology, a NAND gate is implemented with an AND and an inverter, and an OR gate is implemented with an OR and an inverter. So that we could say that within an integrated circuit, NAND and NOR are cheaper in some sense than AND and OR gate. Cheaper in this case means that they need less silicon area to be integrated. A second type of gates are exclusive OR and exclusive NOR gate. An exclusive OR gate, an XOR gate, with this symbol is defined by this table. The XOR of A and B is a function equal to 1 when both inputs are different, when A is 0 and B is 1, or conversely, when A is 1 and B is 0. When A is equal to B, 0, 0 or 1, 1, then the function is equal to 0. The XNOR of A and B is the inverse of the XOR of A and B. So the XNOR of A and B is equal to 1 when A is equal to B and equal to 0 when A is different from B. As regards the XOR function, the symbol used is this one, and sometimes in the case of the XNOR function, the equivalence symbol is used. Now, an equivalent definition is the following. The XOR of A and B can also be defined as being the modulo 2 sum of A and B, and as we already have seen, the symbol is this one. Modulo 2 means that you compute the real sum of A and B in this case, and then you reduce the obtained result to 0 if the result is even, and to 1 if the result is odd. So A plus B. If the result is even, then the XOR function of A and B is equal to 0. If the result is odd, then the XOR function is equal to 1. The XNOR function of A and B is the inverse of the XOR of A and B. Then, with this new definition, it's very easy to define 3 input, 4 input, and so on, XOR and XNOR gates. For example, the XOR function of A, B, and C is the value of A plus B plus C, the real value of A plus B plus C, modulo 2. The XNOR function of A, B, and C is the inverse of the XOR function of A, B, and C. Similarly, the XOR of A, B, C, and D is obtained by computing A plus B plus C plus D modulo 2. The XNOR of A, B, C, and D is the inverse of the XOR function of A, B, C, and D. An important conclusion is that the XOR function is an associative operation, so that in this case it's true that you can build a 3-input XOR gate using for that two input XOR gates. And as regards the XNOR gate, a 3-input XNOR gate can be implemented in this way with one XOR gate and one XNOR gate. Don't forget that the little circle always corresponds to inverse. Let us see now several applications of XOR gates. As a first example, consider a magnitude comparator. Given, for example, two 4-input vectors, A and B, a comparator will generate an output 1 if and only if vector A is equal to vector B. We could use for that this very simple algorithm. If A3 is different from B3, or if A2 is different from B2, or A1 different from B1, or E0 different from B0, then A is not the same as B, so that the output comp will be equal to 0. If the condition doesn't hold, it means that A3 is equal to B3, and A2 is equal to B2, and A1 equal to B1, and E0 equal to B0, so that both vectors are equal and the output is equal to 1. To this algorithm corresponds this circuit. The 4 2-input XOR gates correspond to the 4 conditions. This output is equal to 1 if A3 is different from B3. This output is equal to 1 if A2 is different from B2, and so on. And then there is an output NOR gate that will generate 1 if this input is 0, this also, this one also, and this one also. That means that the output will be equal to 1 if A3 is equal to B3, and A2 is equal to B2, and A1 is equal to B1, and A0 is equal to B0. This is a first example. Let us see a second example, a parity bit generator. Consider an n-component vector A. Its parity bit is an additional bit A n such that the extender A vector has an even number of 1. It is used for error detection purpose, as we will see later. An observation. Consider a vector a k component vector, a k-1, a k-2, and so on, down to a0. This vector has an even number of 1s if, and only if, the modulo 2 sum of all its components is equal to 0. That is to say, if the XOR function of all its components is equal to 0. Thus we can define two algorithms. One, to generate the parity bit. It's very simple. If we compute the XOR function of an-1, an-2 down to a0, if there is an even number of 1s, this XOR function will be equal to 0, so that the new bit an will be equal to 0. On the contrary, if there is an odd number of 1s in this set of components from a n-1 down to a0, then the XOR function will be equal to 1 and the new bit will be equal to 1, so that the extended vector A will have an even number of 1. As regards the parity check, it's just a matter of computing the XOR function of the n+1 components of extended A. If there is an even number of ones, the result is 0 and the error signal will be equal to 0. If there is an odd number of ones, then the XOR function is equal to 1 and the error signal will be equal to 1. Let us see a typical example of application of the concept of parity bit. Consider a system that must transmit 8-bit data from some source to some destination. Before transmitting the information, the parity bit of every 8-bit data is computed and added to the transmitted vector, so that all transmitted data, now 9-bit data, will have an even number of 1. Now, if during the transmission there is an error that modifies the value of an odd number of bits, for example of 1 bit, but also 3, 5, and so on, then on the destination side, the received 9-bit vector will have an odd number of ones, and this fact will be detected by the parity check circuit. The parity generation is done in this example by this circuit with the 7 XOR gates, and the parity check with this circuit that include one more or XOR gate. Anyway, the main application of XOR gate is arithmetic. As a matter of fact, 1-bit adders are the basic components of practically all arithmetic circuits. A 1-bit adder computes two functions, an output carry equal to 1 if and only if the sum of x, y, and carry in is greater than or equal to 2, and a bit sum s that is the modulo sum of x, y, and carry in, so that we can write the value of s as the XOR function of x, y, and carry in. What about the condition x plus y plus carry in greater than or equal to 2? It can be expressed as follows. If x is equal to y and x and y are equal to 1, then the condition surely holds true, because the sum is already, without the carry in, the sum is already equal to 2. If x and y are equal but both equal to 0, then the condition doesn't hold true, whatever the value of the input carry. Then it remains the case when x and y are not equal, 0, 1 or 1, 0. Then it depends on the carry. If the carry in is equal to 1, then carry out will be equal to 1, and if carry in is equal to 0, then carry out will be equal to 0. So that the condition x plus y plus carry in greater than or equal to 2 is equivalent to this condition, x equal to 1 and y equal to 1, or x different from y and carry in equal to 1. And this can be written in this way. carry out is equal to x times y plus, in this case it's the Boolean sum, carry in multiplied by x XOR y. X different from y and carry in equal to 1. So we get those equations to which correspond this circuit. Observe that S is the XOR function of x, y, and carry in. Those two XOR gates implement the 3-input XOR function, and the output carry is equal to x times y plus the XOR function of x and y multiplied by carry in. By the way, those AND and OR gates could be replaced by NAND gates. You can check that the result is exactly the same. So we get a new version of our 4-bit adder with 4 identical sub-circuits serially connected. Obviously, this way to implement adders can be generalized to the case of n-bit adders, for example, connecting 8 versions of this circuit. You will get an 8-bit adder connecting 16 circuits of this type. You will get a 16-bit adders, and so on. In this last section of the two-day lesson, we will see the main application of three-state buffer. First, remember what a three-state buffer is. It's a circuit with one data input x, one data output y, and one control input c. And its working is defined by this table. If c is equal to 0, then y is disconnected. We will also say that the output is in high impedance, and many times high impedance is represented by letter Z. On the contrary, if C is equal to 1, then the output Y is equal to the input X. Similarly, we can define three-state inverters. When C is 0, the output is equal to Z, high impedance, and when C is 1, the output is the inverse of the input. Another possibility is that the control signal is inverted, what is represented by this small circle. Then the output Y is in high impedance when C is equal to 1, and the circuit transmits or inverts the input when the control signal is equal to 0. The main application of three-state buffers are the buses. They are parts of digital circuits used to efficiently transmit data from one point to another one. Let us see an example. Consider 3 components, A, B, and C of a digital system. A could be a memory, B could be an input interface with the external world, and C, a processor. Well, in this case, A and B must be able to transmit data to C, but you cannot connect the outputs of A and B directly to the inputs of C. In order to avoid collisions, three-state buffers are inserted between the A outputs and the set of connections, of input connections to C, and also between the B outputs and the inputs to C. So, if we have to send the data from A to C, then CA must be equal to 1 and CB equal to 0, so that the output of A is connected to the bus lines and transmitted to the C inputs. On the contrary, if you want or if you have to transmit some data from circuit B to the processor, to circuit C in general, then CA must be equal to 0 in order to disconnect it, circuit A from the bus, and the bus is taken by circuit B through these three-state buffers. That means that CB must be equal to, this is the main application of three-state buffers. This table is a summary of the set of main gates we are going to use to implement combinational circuits. Those gates are AND gate, OR gate, inverter, NAND gates, NOR gates, XOR gates, XNOR gates, and three-state buffer. Summary of this lesson: we have introduced the concept of NAND and NOR function and have demonstrated that both NAND and NOR are universal modules. We have also seen what is a XOR function and its inverse, an XNOR function. And finally, we have seen how to define buses using three-state buffers.